We are in Chapter 3, Additional Applications of the Derivative. Section 3.1 is increasing and decreasing functions, and then also relative extrema. A function is increasing if it goes up from left to right, and decreasing if it goes down from left to right. So sketching little graphs of both of these in that space that's provided. If you draw a coordinate plane, draw two of those. I'm going to go ahead and draw a line that is increasing, and I'm going to draw a linear function, which is what we are dealt with before in algebra. And since this is a calculus class, we're going to extend upon this and not exactly have straight lines all the time. So we have an increasing and then also a decreasing function. The next example says determine the intervals on which the function on the graph below is increasing and where it is decreasing. So the first part that we have on a graph, and we read our graphs from left to right, is rising, it is increasing. And then we hit this point up here, which is our maximum, and then the graph begins to fall, and that means it is decreasing. And then at that minimum value, it's going to switch again, and it is increasing. And at the max up here, and then it switches to decreasing. And then at the min, it switches to increasing. So it's asking for where is the function increasing. Let's go ahead and look at that. The first interval we have, and whenever you talk about intervals, remember you always use your x values. And so we have to make sure we use our x values. So increasing, and this graph has no arrows at the end, and that happens a lot with the mini graphs. So if you want to add them in, you can. If there isn't any provided and there's not a solid dot, then it's implied that it goes on forever. So it's increasing from negative infinity until it switches, and it looks like maybe about negative 2.5, negative 2.4. I'm going to go ahead and put negative 2.5. We don't include the point at the top, that maximum value, and the reason why is because at that point it's technically constant. It's not increasing nor decreasing, so it's going to be a parenthesis. The next interval we have where it's increasing is right here, and it goes from x is 0 to x is 2. And we symbolize this by a U for union, and then our 0 value for our x to our 2 value for our x. Again, we use x values when we talk about our intervals. And then that last interval that we have is going from this minimum value and on. So we have this whole part of the graph here. And it looks like that's about 3.5. So I'm going to go and say union. And we'll say 3.5 comma infinity, since it does go on forever. We also need to state where it's decreasing. And it is decreasing from this maximum value here, from negative 2.5 is what we called it, all the way down until 0. So from negative 2.5 until 0. Again, we do not include those endpoints because it's neither increasing nor decreasing. And then we have a second interval, so union, and it goes from 2 to about 3.5. So 2, 3.5 will be my intervals where it is decreasing. And if you notice, it is switching from increasing to decreasing at minimums down here and at maximum points that are up at the top. So kind of make sure you're aware of that, because that's going to help you out later on in this semester. So the next thing it says, let f of x be a function defined on the interval from a to b, and let x1 and x2 be two numbers in the interval. Then increasing intervals have a positive slope in which f of x2 is greater than f of x sub 1 for x2 greater than x1. And again, we saw that in a picture. It has an increasing slope. And decreasing intervals have a negative slope, which means that f of x2 is less than f of x1 for x2 greater than x1, meaning that it falls as you read that from left to right. And then we also have horizontal intervals have 0 slope, which is new. We didn't see that in the picture up above, which means that f of x2 equals f of x1, meaning those y values are the same. And that means that we would have a horizontal line, and that has 0 slope. Next definition that we have is called a critical number. Critical number for a function f are those numbers c in the domain f where f prime of c is either equal to 0 or f prime of c does not exist. Critical numbers are the maximums and minimums of f of x, and they are the x-intercepts of the derivatives. Critical points, so this time it's a point. And anytime you have the word point, that means that we're talking about an ordered pair, which means we have x comma y, whose x-coordinate is a critical number and the y-coordinate is f of c. So we have a graph on here that you can look at that shows you when f is decreasing, our derivative is less than 0. When f is increasing, our derivative is greater than 0. And then we have at our minimums and at our maximums, put an equal sign in there, we have that our derivative is equal to 0. Likewise, whenever you have a flat part of your graph that's horizontal. On the next page, we have the increasing and decreasing test. It says, let f of x be a differentiable function on the open interval from a to b if f prime of x is greater than 0, so if that derivative is positive for x in that interval from a to b, and so the derivative is positive, then f of x is increasing on that interval. Likewise, if f prime of x is less than 0 for x in a and b, so the derivative is negative, then f of x is decreasing. So another way to determine if a function is increasing or decreasing on specific intervals, besides looking at the graph, we can look at the derivatives. And a lot of times that's easier than trying to graph an equation and figure out where the graph is, especially when you have large numbers and it's difficult to graph. So the next thing says applying the increasing and decreasing test using derivatives. First thing we're going to do is find the critical numbers, and this is going to be where your derivative is equal to 0 and where the derivative is undefined. Second thing, we're going to use the critical numbers to find open intervals. So we're going to split up our domain into these open intervals, choose an x value of each interval to test, and substitute that into f prime of x. So this is step 3. You're going to substitute in something that's inside the interval into your derivative. And from there, what we need to know is that if the derivative is greater than 0, then f is increasing on that interval. And if f prime of x is less than 0, then f is decreasing on that open interval. And if the derivative is equal to 0, then f is constant on that open interval. So the first example that we have says, find the intervals on which f of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5 is increasing and where it is decreasing. First thing that we have is this is a polynomial, and since this is a polynomial, our domain for this function, like we saw before, is going to be all real numbers. So in order to find the intervals where this is increasing and where it's decreasing, I'm going to go ahead and use our calculus rules. And this says that we need to find our derivative, we need to figure out the critical numbers, and then we have to break this interval, this domain into intervals and test to see if it's positive, negative, or 0 with the derivative at those values. So I'm going to go ahead and find my derivative first. So f prime of x is equal to, and taking our derivative, we end up with 12x to the 3rd minus 12x squared minus 24x. So that's our derivative. That was the first thing that we need in order to find our critical numbers. From here, we are going to set our derivative equal to 0. To solve this, I'm going to factor out a 12 and an x, since that's our common factor. And I have x squared minus x minus 2 equals 0. So then we have 12x, and then we have x minus 2, x plus 1 equals 0. Solving this, we're going to set each of these 3 factors equal to 0. So we get x is equal to 0, x is equal to 2, and x is equal to negative 1. So these that we found, all these 3 numbers that we have, are our critical numbers. So critical numbers. And we also have to look at where our derivative is undefined. And it's never undefined. And the reason why is because we have a polynomial for our derivative up here. And the polynomial has a domain of all real numbers. So since the domain of our function was all real numbers, I'm going to go ahead and draw a number line that includes my domain, which is all real numbers, and put some arrow tips on the end. And I'm going to break this up into open intervals. And it says use the critical numbers, which I've underlined. And so we have -1, we have 0, and we also have 2. So from here, I need to pick a test value, and I need to test it into my derivative. So I need to pick something that's smaller than -1. I'm going to go ahead and find f of -2. I need to substitute in something that's in between -1 and 0. So I'm going to go ahead and substitute in -0.5. I also want you to notice that we're substituting these into the derivative, which is up here, and I'll go ahead and box that. And we need to substitute it into that function. And if it's positive, it's increasing, negative, decreasing. If it's 0, then it is constant. So the next one between 0 and 2, we're going to go ahead and find f prime of 1. And something larger than 2, we'll go ahead and say f prime of 3. So from here, you need to substitute in these values into our derivative function to figure out if those intervals are positive, if they're negative, or if they are 0. So when you substitute in -2 into my derivative and you work that out, you get a negative answer. If you substitute in -0.5 into the derivative, you get a positive answer. Substituting in 1, you're going to get a negative answer. Substituting in 3, we get a positive answer. And it does not always switch like this. This is just our first example. And so where is this function increasing? And it's increasing when my derivative is positive. And that's going to be from -1 to 0, union from 2 to infinity. And when is it decreasing? Well, it's decreasing from -infinity to 1 and from 0 to 2. So from -infinity to 1 and from 0 to 2. The next thing that we have is the relative maximums and minimums, and this says let c be a number in the domain of function f. Then f of c is called a relative or a local maximum if f of x is less than f of c for all x in the interval a to b. And it's also called a relative minimum, or you can also call it a local minimum, if f of x is greater than f of c for all x in that interval. If a function f has a relative extreme, or a maximum and minimum, at c, then c is a critical number, or c is an endpoint of the domain. Relative extrema is a relative maximum and a relative minimum of the function. And we'll see that word extrema quite often. That means if it ever says to find extrema, you're finding both maximums and minimums. A polynomial of degree n can have at most n minus 1 relative extrema. So if you notice, there's a picture over here on the right, and that picture has mins and maxes labeled, but I want you to note that all of these minimums are called relative minimums, and all of these maximums are called relative maximums. And another word that you'll see in different textbooks is local instead of relative. So the example on the next page says find the location and the values of all relative extrema for the functions f of x with the graph below. So I'm going to go ahead and look at our graph, and I'm going to go ahead and label them. Where do we have relative extremas? I'm going to read the graph like I read a book. So the first one we have is up here at our max value, that point. We also have another one up here when x is 0. So there's another relative max. And then we also have one here at this point, and we'll say relative max. So our relative maxes are at, and I'm going to go ahead and write these as ordered pairs. So this was -1, -2, -3, -4, and -5. So we have a relative max at -5, 1. We have another one at 0, 3. And then our last one is going to be, if you count this out, 1, 2, 3, and then 4, is going to be at 4, 1. Next thing we have is our relative mins. And our relative mins we'll go ahead and label first on our graph. So the first one that we have is this point down here. So we have a relative min. We have a second one here. It's our relative min. And then we have a third one over here, that endpoint right there is a relative min also. We don't have one on the other endpoint because if you notice, this one has an arrow tip pointing off and saying that that doesn't ever end, so we don't have a minimum value there. So our relative minimums are going to be at -3, -2 is the first one. Our second one is going to be at 2, 0. And then our third one is going to be at 6. Count that out. So at 6, -2. We can algebraically determine where the relative extremas are located using the first derivative test. So the first derivative test says let C be a critical number of a continuous function f of x. Then f prime of C changes from positive, so when it changes from positive to negative. So if it goes from increasing to decreasing, we have up here at the top a relative maximum at C. Whereas if the derivative changes from negative to positive, down here at the bottom we have a relative minimum at C. If f prime of x has no change in the sign from the left and the right of C, then f has no relative maximum or minimum at C. So a visual approach to the first derivative test is given below. Let C be a critical number. And so on the first one, you can see that there is going to be a relative maximum at C. The second one, there's going to be a relative minimum at C. And then if it's increasing on both of those, on the left side of C and on the right side of C, both those derivatives would be positive. That means that we do not have either, so I'll put down none. If the derivative is negative on the left side and on the right side of C, our critical number, then that means we do not have a relative minimum or relative maximum at C. So I'll go ahead and put down none. Steps to using the first derivative test to analyze critical numbers given f of x. Step 1 says to find all critical numbers C. Step 2 says using a number line, break the domain into open intervals using the critical numbers. Step 3 says determine whether f is increasing or decreasing on each interval. And to do that, we're going to select one value in that interval and substitute it into the derivative. And if that value is positive or if it's negative, we'll tell if that function is increasing or decreasing on that open interval. Step 4 says if there is a change from increasing on AC to decreasing from CB, there is a relative maximum at f of C. If there is a change from decreasing to increasing on C, B, there is going to be a relative minimum at f of C, just like how it's illustrated up above. The next example that we have says find the location and the values of all relative extrema for the function f prime of x with the given graph below. So first I want you guys to notice that this is not the graph of our original function. This is the graph of the derivative. And since it's the graph of the derivative, that means that our critical values are going to be where the derivative is equal to 0. So critical values, I'll abbreviate as CB, are going to be where, just like how it is by definition, where our derivative is equal to 0 or where it's undefined. I don't have any spots on my graph right now where anything is undefined. It is a polynomial or a graph of a polynomial on here. So this means that this would be where the derivative is equal to 0, or where the y values would be equal to 0 would be our x-intercepts. So the next thing that we have, it says find the location and the values of all relative extrema. So if you notice this part, reading the graph from left to right over here, from negative infinity to negative 4 is positive. It is above the x-axis. And then it switches down below, and I'll kind of make that line a little different. And these are negative values, those y values. The derivative is going to be negative. And then it switches to being above the x-axis, and this is where it is positive. And then it doesn't switch, but it does have an intercept, and this last part over here is also positive. So I'm looking at the sign. Since this is a graph of the derivative, that means that my x values are what I'm substituting in, and my y values aren't y this time or f of x, they're actually f prime of x. So we're looking at the sign of those. So if you notice, we are switching from being increasing from a positive to a negative slope, or from being above the x-axis to below the x-axis at negative 4. So we'll say at x equals negative 4 is where that x-intercept is, and where our graph is switching, our derivative is switching from being positive to negative. And at that point we would have a relative max. So the next x-intercept that we have is at negative 2, and from that, since we read a graph just like how we read a book, it's going to go from being decreasing to increasing. And doing that happens at x equals negative 2. And since it's going from decreasing to increasing, that's a minimum. So we have a relative min at x equals negative 2. What about at 3? So at x equals 3, it goes from being above, so increasing, to after it is also increasing. So there is none at, none at x equals positive 3. Yes, it is an x-intercept, and those are usually where our critical values are and where we are determining where we have a relative min or a relative max, but from that one we don't actually have one. The next example that we have says find the x value of all points where the function defined as follows has any relative extrema. Classify them as being relative maximums or minimums. And really quick, it does say to only give us the x values, so we don't need to go ahead and find the y, but we can discuss that also. Part A, f of x is equal to x squared plus 8x plus 5. In order to find the x values of our point where there is any relative extrema, I need to go ahead and find my critical values, and in order to do that I need to take my derivative and figure out where this is equal to 0 or where it is undefined. So the derivative of my function would be 2x plus 8, and I can set this equal to 0 and solve this, and we'd have 2x is equal to negative 8. Dividing by 2 we get x is equal to negative 4. And from here I know x is equal to negative 4, and I also know that the derivative f prime of x is not undefined anywhere. So we can say that the only critical value that we have would be at x equals negative 4. And so I'm going to go ahead and take my number line, and I'm going to have a number line that includes all of the domain, and the domain of my function is equal to all real numbers. So I'm going to go ahead and have a number line that includes all real numbers. And the only critical value that we have is negative 4. So my critical number is negative 4. And from here I need to substitute in something smaller than negative 4, and I will substitute in negative 5 into my derivative. And something larger than negative 4, 0 is an easy value to pick. So if you were to substitute this back into your derivative for 0, you get positive 8. And that is positive, so that means that that interval is going to be increasing. And when I substitute in negative 5, we actually get that that interval is negative, which means that it is decreasing. So it is switching here. So it goes from decreasing to increasing, and we'd have a relative min. So we would have a relative min at x equals negative 4. and this problem only does ask for the x values, but if you needed to find the y values, you would take -4 and substitute that into your original function. Your original function is up here, and I'll go ahead and circle that. So substituting this in, because sometimes they do ask for it as an ordered pair, or if it doesn't say just the x values, then it's implied that it would like both of those. And -4, -11. And there's also multiple ways to write this. So you could say f of -4 is equal to -11. They also sometimes will write it out as almost like a sentence, but different ways that the same problem can be represented, so make sure you're aware of that. The next example, which is not labeled as B, go ahead and label it B, and we will do this one in class, so go ahead and circle that. And then the next page has an example that says the revenue derived from the sale of a new kind of motorized skateboard, T weeks, after it's been introduced, is given by, and we have the revenue function here, where T is going to be between 0 and 63, and including those two values, millions of dollars. When does maximum revenue occur? And what is the maximum revenue? So in order to figure out your maximum, you could graph this and look at the graph. However, to graph something like this by hand would be difficult. So a more appropriate and capable way of solving this would be to take a derivative and find our critical values, our critical numbers, and that's going to be either where we have relative maximums or minimums. So going ahead and taking the derivative of r of t, and this is a quotient, so I need to use the quotient rule, and the quotient rule goes to the denominator, which is t squared plus 63, times the derivative of the top, which is the derivative of the numerator, which is going to be 63 minus 2t, minus the top, which is 63t, minus t squared, times the derivative of the denominator, and the derivative of the denominator is going to be 2t. This is divided by the denominator squared, which is t squared plus 63, quantity squared. From here, we need to distribute, and make sure you distribute the negative, and you combine your like terms. And when you do that, you should arrive at negative 63t squared minus 126t plus 3,969 divided by t squared plus 63 quantity squared. And so in order to find our critical values, we need to set this equal to 0. And so if we set this equal to 0, we can go ahead and solve this, multiply both sides by the t squared plus 63 quantity squared. And I also, in the numerator, if you notice, you can actually divide all those terms by negative 63. So I'll go ahead and factor out a negative 63, and when we do, we are left over with t squared plus 2t minus 63, and this is equal to 0. This also factors, so you're able to factor t squared plus 2t minus 63 into t plus 9 and t minus 7. And so from here you can get your critical values are going to be at t equals negative 9 and t equals 7. And then our derivative r prime is undefined nowhere, and the reason why is if you were to set that denominator, t squared plus 63 squared equal to 0, and solve it, you'll figure out that that is going to have a square root of a negative value, which is not real. The other thing that we need to look at here is that this is a word problem, and this is our revenue that we're talking about, and t is written in weeks, and since t down here is negative 9 and positive 7, hope you guys realize that t, our time, cannot be negative, so t must be positive, so that's why we only are going to deal with positive 7. And when I draw my number line, I'm also going to make sure that when I draw it, technically it could be all real numbers, but for this problem, since we are dealing with time, I'm going to go ahead and start it at 0, since time is not negative, and I'll go ahead and put 7 on there for our critical value on here, our critical number. So in order to figure out if this is a relative max or min, we need to go ahead and substitute in something smaller than 7. I'll substitute in 1 into my derivative. And something larger than 7, and we'll go ahead and substitute in something easy like 10. But definitely any value that you want that's larger than 7. From here, you're going to substitute that value into your derivative, which I'll box here. So substituting in 1, you do get a positive value, and so that means that this interval from 0 to 7 is increasing. And then from 7 on through, you actually get a negative value if you were to plug in 10 into your derivative. So that means that it is decreasing. So this goes from increasing to decreasing. So this point up here at the top is going to be our relative maximum. So we have a relative max at t is equal to 7. So the question here was, when does the maximum revenue occur? And the max revenue, and make sure you guys put your units. So this occurs at t equals 7, and our units that we have here is weeks for our time. And it also says, what is the maximum revenue? So in order to find the maximum revenue, we need to substitute 7 back into our original revenue function, which is up here at the top and typed for us. And when you substitute that in and work that out, you should get 3.5. And the units that we are going to have with that is going to be in millions of dollars. So millions of dollars. The next section that we have is 3.2, which is on concavity and points of inflection. Concave upwards. If a graph of f lies above all of its tangent lines on an interval, a function is concave up on an interval if it opens upwards on that interval. So if you look at the picture, the diagram right below, if you were to draw tangents, you'll notice that on the concave up part, that curve lies above all tangent lines. Most students just think of concave up as making a happy face. And then concave down says if the graph of f lies below all of its tangents on that interval. So if you were to draw your tangents here, you'll notice that that curve is below or underneath all of those tangents. And it says a function is concave downwards on the interval if it opens downwards. And a lot of times students think of these as sad faces. So if you notice here we have concave up, and we have concave down. And then you'll notice another thing on the graph, and the definition of it's right below. It says the point of inflection. The point, and I want you guys to realize it is a point, meaning that you need to have an x and a y, is an inflection point of f of x if f of x is continuous at c, and this is where the concavity is going to change. So if you notice, that's where it's changing from concave up to concave down in the diagram. The next example says the following is a graph of f of x. Identify the inflection points and intervals of concave up and concave down of our function. So if you go ahead and look at this, you'll see that we have some inflection points, and our inflection points are where the concavity is changing. So let's go ahead and look at where this is concave up first. So concave upwards. And this is where the graph is opening up, and it is concave up. I'll go ahead and put a CU for concave up. And that goes from A to B. So from A to B, we have concave up. We also have another interval, and that other interval is going to be, so I'll put a U for union. We go from B to C is also concave up. So from B to C is concave up. And then again, we switch over here on the far right, and we go from D on up to infinity. So union D to infinity. We are concave down on, and I'll go ahead and highlight these, from, this is going to be from negative infinity to A, and then also from C to D. So from negative infinity, And again, remember, if there is no arrow tips, add them in if it makes you feel more comfortable with the graph. Negative infinity to A, union from C to D. Also, those inflection points are where they are changing, and so we would not include those, and that's why we have parentheses on all these. Also notice that the value at C is an asymptote and there is no value there. It also asks for us to list the inflection points. And so the inflection points that we have, so where is it changing concavity? It changes at A, it goes from concave down to concave up. And so our point would be A comma f of A. We'd have to substitute in whatever that value is. It does not change at B because it goes from being concave up to concave up, so that did not change. However, it does change again at D because it goes from being concave down to concave up. So we'll go ahead and say and at D comma f of D. On the next page, it says another way to think about concavity is to examine the derivative. Let f of x be a differentiable function on an open interval, then f of x is going to be concave up if the derivative is increasing on the interval, and concave down if the derivative is going to be decreasing on the interval. And so you can see that on the slopes if you look at those in the diagram that's given. And we have our concavity test, which says let f of x be a differentiable function on an open interval AB. Then f of x is concave up if the second derivative is greater than 0, and concave down if the second derivative is less than 0 for all x in those intervals. So steps for finding inflection points and intervals of concavity of our function. First thing is to find all x values where the second derivative is 0 or undefined. These are not the inflection points, but these are possible. So make sure you highlight the word possible. They're possible inflection points. 2, using a number line, break the domain into open intervals using the possible inflection points. So just like how we've done before, but this time using the possible inflection points. Step 3 says choose a test value from each interval to substitute into your second derivative to determine if the second derivative is positive or negative. On intervals where the second derivative is positive, that's where we have concave up. We would go ahead and put, I'm going to abbreviate it as CU. And then where the second derivative is negative, this is where we are concave down. Step 5 says if concavity changes between consecutive intervals from AC and CB and f is defined at x equals c, then the coordinate point c comma f of c is an inflection point. So the next example that we have says find the points of inflection of, and we have a function there. Our function is a polynomial, and determine the intervals where the function is concave up and concave down. So since we have a polynomial, our domain here is going to be all real numbers. So go ahead and write that down. And so in order to figure out where this is concave up and concave down, I don't only have to find the first derivative, we have to find the second derivative. So our first derivative, taking a derivative of this, we arrive at 15x to the 4th minus 20x cubed. And then we need to find our second derivative. And so our second derivative is going to be 60x cubed minus 60x squared. And in order to find our possible inflection points, we need to set this equal to 0 and solve it. We can factor out a 60 and an x squared. We're left over with x minus 1 is equal to 0. Solving each of these, we get x is equal to 0 and x is equal to 1. These are going to be our possible inflection points. So possible, and again inflection points, and I'm going to abbreviate that by IP. Inflection points only occur where we have a change in concavity, and right now we don't know yet if these are changing concavity at 0 and at 1. So in order to figure that out, I'm going to go ahead and draw a number line again. My domain is all real numbers like we stated, so I'll just put arrow tips on the ends of both of these. And I'm going to put my possible inflections on, so I have 0 and I have 1. I'm then going to select a value in each interval, and this time substitute into my second derivative function, which I will go ahead and box. So I need to substitute into that function. So I'm going to go ahead and substitute in something smaller than 0 into my second derivative, so I'll substitute in -1. Something between 0 and 1 into my second derivative, I will pick 0.5. And then something larger than 1, again, anything can do. I'm going to go ahead and just select 2. So on your calculator, take a moment, substitute those in. When you substitute in -1, you should get that is going to be a negative value. Since it's negative, and I'm talking second derivative, that means that it is concave down. For the next interval between 0 and 1, when you substitute in 0.5 into the second derivative, you also get that that's negative, and that means that it is concave down. The next interval, which goes from 1 to infinity, when you substitute in 2, you're going to get that it is positive, which means that it's concave up. So we don't have 2 inflection points. We actually only have 1 inflection point, and our inflection point is going to be at 1, and the reason why it's at 1 is because it changes from being concave down to concave up. And so we have an inflection point at 1, comma f of 1. In order to figure out that y value, since we do need that because it's a point, you need to substitute 1 back into your original function up here. And when you substitute in 1, you get a value of -1. The next example that we have, we're going to go ahead and circle and work on that one together in class. On the next page, we have the second derivative test. The second derivative test says let c be a critical number of f of x, and suppose the second derivative is continuous near c. So c is going to be our critical numbers. Then substituting that into the second derivative, if the second derivative is positive, which means that it is concave up, that means that at that value of c, we have a relative minimum. So if it's concave up, we have a minimum, a relative minimum. Likewise, the second bullet point says if the second derivative is less than 0, so if it's negative, that means that it is concave down. And that means at that value of c, we actually have a maximum, a relative maximum, when it's concave down. So we have a relative maximum if the second derivative is less than 0. If the second derivative is equal to 0, the test is inclusive, and f of c might be a relative max, a local min, or neither. So we have to use the first derivative test. So this only works, again, if you get a second derivative that's either positive or negative. Steps for using the second derivative test to analyze critical numbers given f of x. First thing we need to do is find the critical numbers by figuring out where the derivative is 0 and undefined. 2, substitute each critical value c into the second derivative to determine the sign. Again, if the second derivative is positive, then we have a relative minimum. If the second derivative is negative, we have a relative maximum at c. So the first example that we have on here says, determine whether each critical value of f of x, which equals 2x cubed plus 3x squared minus 12x plus 1, is a relative minimum or a relative maximum. This time it tells us to use the second derivative test. So going ahead and doing that, we have our first derivative, which is going to be f prime of x. And taking the derivative of our function, we end up with 6x squared plus 6x minus 12. To find our critical values, I need to set this equal to 0. I can factor out a 6. When I do, I can factor that remaining polynomial. And so I have 6 parentheses x plus 2. And I have x minus 1 is equal to 0. Separating those and solving both, I get x is equal to -2 and x is equal to positive 1. These are our critical values, or our critical numbers. Also, this derivative is undefined nowhere, so that means that these are the only 2 critical values that we have. So from here, I need to find my second derivative, which if I find my second derivative, I'm going to arrive at 12x plus 6. And so in order to figure out if I have relative maximums or relative minimums, I need to substitute in my critical values into my second derivative. So I'm going to take my second derivative and substitute in -2. And then I'm going to take my second derivative and substitute in +1. And again, we are substituting these into your second derivative, which is down here at the bottom. So 12 times the -2 plus 6 is going to work out to being -6. Since this is negative, that means that it is concave down. So go ahead and draw a concave down graph if you're more visual. Since it's concave down, that means that that value at C, so at x equals C, in this problem it's x equals -2, our critical value or critical number, is going to be a relative max. And so we have our point, which is going to be -2 comma f of -2. Substituting this in, we have -2 comma 2. Again, you need to substitute that back into your original function up at the top that's typed. Likewise, when you substitute in 1, you're going to have 12 times 1 plus 6, which works out to be an 18, which is positive, which means that this is concave up. And since this is concave up, that means we have a relative min at our critical value. And so we have at x equals 1, it is concave up, and so we have a relative min, and that relative min occurs at 1 comma f of 1, and then substituting that in, we have 1 comma f of 1 is going to work out to be -6. So the next thing that we have is called the Law of Diminishing Returns, and this states that C, comma f of C is an inflection point and is called the point of diminishing returns when x is less than C, concave upwards, rate of change is increasing, output increases at a faster rate with each dollar spent, and when x is greater than C, we are concave down and the rate of change is decreasing. Output is smaller with each dollar spent. And so you can see that point inflection is the point of diminishing returns. So we have an example right below that we are going to go ahead and circle, and we will work on this one together in class. On the next page, we have a summary of analyzing graphs of our derivative and our second derivative, and I will leave that for you guys to look at on your own. It's kind of a summary of what we just went through. The next section that we have is section 3.3, which is on curve sketching. This section discusses sketching a comprehensive graph given any function f of x. Steps to graphing a function f of x. First thing is to find the domain of f of x, where f of x is defined. The second thing is to find the asymptotes, the vertical and horizontal. And just as a reminder, to find your vertical asymptotes, we're going to go ahead and set our simplified function. So I'll put down simplify first. And once you have your simplified function, you're going to set your denominator equal to 0 and solve. So this is back from review and also back from Algebra 2. And then we also have our horizontal asymptotes. In your horizontal asymptotes, we have a few different ways to deal with them. We'll go ahead and look at the calculus way, which is to look at the limit as x approaches positive infinity and negative infinity of our function. This is also both covered in the chapter 1 notes, so if it seems a little rusty to you, make sure you go back and look at those. Step 3 is to find our derivative, f prime of x, and the critical numbers. Create a sign chart, and so we're going to call it a sign chart, which is what we've been doing, of our derivative to find the intervals of increasing and decreasing and our local extrema. 4 says to find the second derivative and the possible inflection points, and create a sign chart for our second derivative to find the interval of concavity and our inflection points. The next thing that we have, step 5, says to create one number line to summarize steps 1 through 3. Use idea of pictures below to help you out. Step 6 is on the XY plane. Plot extrema values, inflection points, asymptotes, and intercepts. And then step 7 says to sketch with detail each portion of the graph between extrema, inflection points, and asymptotes. So from here you can see that when it is increasing in concave up, decreasing concave up, likewise increasing concave down, and decreasing concave down. And remember, increasing and decreasing is told to you guys by your first derivative, and second derivative tells you if it's concave up or concave down. The example on the next page says to sketch the graph of f of x equals negative x cubed plus 3x squared plus 9x minus 10. So the first thing is what is the domain? And the domain of this function is all real numbers. It is a polynomial. And so I'll go ahead and put all real numbers down. And then the next thing we're going to do is we're going to find our intercepts. I'm going to go ahead and zoom in here just to be able to write a little bit clearer. To find your intercepts, to find our x-intercept, we're going to go ahead and set y equal to 0. So we're going to have 0 equals, and it's negative x cubed plus 3x squared plus 9x minus 10. And then from here, see if you can factor this. See if you can group them and factor it. And if you realize you can't easily, so since it's too difficult to do, so I'll put down too difficult, I'm just going to skip this. This one is not an easy one to do, and not all the problems are going to be so precise to see. This might mean that this has intercepts, but they're not. The x-intercepts are going to be not very pretty, maybe like the square root of 7 or something along those lines. Or maybe it doesn't even have any x-intercepts. So for right now, we'll just say it's too difficult to find. To figure out our y-intercepts, so that's a little bit easier. So the y-intercepts is where you're going to set x equal to 0. And when you do that, you get y is equal to negative 10 when you set x equal to 0. And so we have an ordered pair of 0, negative 10. And that is our y-intercept. And then do we have any asymptotes? And no, because this is a polynomial, we have no asymptotes. So no asymptotes. Usually you arrive at asymptotes, both horizontal and vertical, whenever you have a rational function, so a function over another function. So from here, I need to find my first derivative in order to find my critical values and also figure out where I have intervals of increasing and decreasing. So my first derivative is going to be negative 3x squared plus 6x plus 9. I'm going to set this equal to 0. Also note that the derivative is not undefined anywhere, so our only critical values are going to be where the derivative is equal to 0. From here, you guys can factor out a negative 3. When you do, you have x squared minus 2x, and then minus 3 is equal to 0. I'm going to go ahead and factor that remaining polynomial, and when I do, I have negative 3 times x minus 3. And then the other factor is going to be x plus 1, and we'll set that equal to 0. Solving this, we have critical values of a 3 and a negative 1. And I'll go ahead and label this CV for critical values or critical numbers. So this is going to help us figure out our intervals of increasing and decreasing, and we'll do that in just a moment. The next thing I need to find is to figure out where my possible inflection points are. That will help me figure out where it's concave up and concave down, and then also figuring out the exact inflection points. To do that, I need a second derivative. So I'm going to look at the first line of my first derivative, and I'll go ahead and box it. And taking a second derivative, taking the derivative of a derivative, we get negative 6x plus 6. Setting this equal to 0, I'll find my possible inflection points. Also note that there is no place where the second derivative is undefined. Solving this, we're going to get that x is equal to 1. And this is my, not an inflection point, but this is a possible inflection point, an IP for inflection point. So from this, I'm going to go ahead and create one giant number line. And the domain of my function was all real numbers, so make sure that you have that all included. I'm going to go ahead and put on my critical values, which is at 3 and a negative 1. and also my inflection point, which is at 1. So I have -1, we have +1, and we have 3. So I need to pick a test value. And I'm going to not just do this for my first derivative, I'm also going to do this for my second derivative to figure out my intervals of concavity. So to keep my lines a little bit cleaner, I'm just going to go ahead and separate these, and I'll just use my highlighter to separate these intervals. Makes it a little bit easier for me to see where it's switching and what's going on in each of these intervals. So let's look at the first derivative first. So I'm just going to write f prime of x over here on the side. And I'm going to pick test values, and I'm going to pick something smaller than -1. So we'll say let's test -2. Something between -1 and 1, definitely 0. So test 0. Between 1 and 3, I'm going to test +2. And something larger than 3, we'll just say let's test 4. But again, it doesn't have to be the same numbers I'm selecting, just making sure it's in that interval. So substituting in -2 into my first derivative, I do get it's negative, and since that's my first derivative, that tells me if it's negative, it is a decreasing interval. When I substitute in 0 into my first derivative, which is boxed, or you can look at when it's simplified and factored out, but when I substitute in 0, I get 9, and that is positive, which means that it is increasing on that interval. Substituting in 2, I also get that it is increasing. And then substituting in 4, we get a negative value, which means that it is decreasing. I want you guys to notice at 1, it doesn't change from increasing to increasing. And you can either notice that by just putting the work into, or also looking at the critical values and realizing that 1 isn't a point where it would change from increasing to decreasing. That was my inflection point, possible inflection point. So that's why those are both increasing on both sides. If that seems a little bit too deep for you, that's okay. A lot of times it takes some practice to kind of get this down and have a more of an understanding of it. So now we need to look at the second derivative. So looking at the second derivative, and I'll go ahead and write that up here. So I have one single sign chart or number line. And looking at my second derivative, and I'm going to go ahead and I'll circle that one down here. I need to substitute in something like -2, which was the value I chose to pick. And when I do, that is going to give me a positive value, which means that this interval is going to be concave up. When I substitute in 0, I get 6, which is positive, which is concave up. When I substitute in 2, I get -6, which is going to be concave down. And then substituting in 4, I also get that it's negative, and that is also concave down. I want you to notice that the only value of where this would switch concavity is at my possible inflection points, which is at 1. So from here, the first interval from -infinity to -1 is going to be concave up and decreasing. So if you can imagine a decreasing function that's concave up, will look something like this. You can look at the pictures that were given to you guys in your notes up above, the 4 different diagrams of this. The second one says that it is increasing, so imagine an increasing line, but make that have a concavity of concave up. The next one is increasing, so also increasing like this. However, let me erase the line, it would be concave down. So something along these lines. And then the last one is decreasing and concave down, so something along these lines. From here, I'm going to put the ordered pairs that I know. We don't know too much. We do know that we have a point at 0, -10. I'm going to go ahead and draw my graph counting by 2.5. So that means I'm going to have -5 down here, -10, and then -15. Likewise, going in the positive direction, we have 5, 10, and 15. And then I'm going to keep my x values just counting by 1s. So I'll just leave that just as normal. If you want to put those numbers in, you definitely can. So I have one inflection point, and that occurs at where our concavity is changing, and our inflection point is going to occur at 1, f of 1. Which if you were to substitute in 1, you're going to arrive at 1, 1, We also have a function going from decreasing to increasing, so we have a relative min, and the relative min is going to be at -1 comma f of -1, and when you substitute in -1, you arrive at -1 comma -15. And then likewise, we're going to have a relative max, and our relative max is at 3. It goes from increasing to decreasing, so we do have a relative max at 3. And substituting in 3 into my function, which is the original function that we have up here at the top, and typed, we're going to get 17 as our y value. So I do have a few points that I can put on. I know that my y-intercept back up here is 0, -10, so I'll put a point there. I know that I have an inflection point at 1, 1, which is a little difficult to graph with our axes being so spread out. And then we also have a value of a relative minimum at -1, -15, and a relative max at 3, 17. So again, do the best that you can and put those numbers in. From here, we're going to connect these the best that we can. So remember, this is our relative max up here at 3, so I know that it would go back down. Likewise, at -1, -15, we are going to have a relative min, so drawing that line up. You can see that we would have 2 x-intercepts, however I don't really know what values they are because that was too difficult to solve. So curve sketching is definitely a long process, a lot of steps to go through. Definitely test your knowledge about everything that we've learned so far in the class. The next example says to sketch a graph of f of x equals 3x divided by x minus 2. So this problem, the domain is going to be all real numbers except for at +2. So I'm going to say -infinity till 2, and then from 2 to infinity. It's where that denominator is equal to 0, and we can't have 0 in the denominator. So the next thing I'm going to do is I'm going to zoom in here, and we're going to find our intercepts. So in order to find our y-intercept, we're going to set x equal to 0. And so when I set x equal to 0, I'm going to have 3 times 0 over 0 minus 2. And when I do this, I'm going to get y is equal to 0. So I have a point 0, 0. I'm going to underline that so we don't lose it. And then to find my x-intercept, I'm going to set y equal to 0. Solving our equation, you're going to arrive at x is equal to 0, which gives us the same value that we have up above. So next question is always asymptotes. And so we do have some vertical asymptotes. And so vertical asymptotes is going to be where your denominator, and note you cannot simplify this function at all, would be equal to 0, which means we have an asymptote that's vertical at x equals 2. And then our horizontal asymptotes is where we look at the limit as x approaches positive and negative infinity. So I will look at positive infinity first of our function, which is 3x over x minus 2. So to deal with this, back from chapter 1, we're going to divide all of our terms by the degree of the largest variable that we have in the denominator. So this is still going to stay limit of x equals x approaches infinity. Dividing all of my terms by x's, I'm going to have x divided by x, which is just 1, 2 divided by x, and then 3x divided by x is just 3. And this is going to simplify to 3 over 1, or 3. This is going to be the same for as x approaches negative infinity. I'll let you guys figure that one out on your own and ask if you have questions. So that means that we have a horizontal asymptote of y is equal to 3. The next thing that we need to do is find our derivative. And from here, finding our derivative, you need to use your quotient rule. And after we find our derivative, we need to find our second derivative. So I am going to circle this and we will continue working on this problem together in class. But see if you can find the first derivative on your own and those critical values, and then also the second derivative and the possible inflection points that we would have.